Here's a very brief introduction to the chromatic number of a graph. The chromatic number is related to colorings, and unless it's specified otherwise, always assume that a coloring a graph refers to a coloring of its vertices. So, for instance, we could color each of these vertices in a different color. Of course, we could color them all with the same color too. And normally when we're talking about a coloring, though, we mean a proper coloring, which means that no edge can have two ends the same color. So again, when we talk about a coloring, we usually mean a vertex coloring, but we don't say so, and we usually mean a proper coloring, but we don't always say so, and you have to figure it out from the context. But that's the hard part. Here's a few examples of graphs where it's easy to find the chromatic number. I think I forgot to say that the chromatic number is the smallest number of colors you need to create a proper vertex coloring. So if you start assigning colors randomly, you may not get the smallest number, but your chromatic number, if there are any edges in your graph, it'll always have to be at least 2, because any edge you have has to have 2 different colors at each end. And when we have a path like these two graphs I have at the top, each of these connected components is a separate graph in my picture, we can just alternate blue and green all the way along the path, and so the chromatic number of this is just 2. And the same with this other path that I drew. Doesn't matter that they're different 2 colors, of course, the chromatic number is still 2. And this first cycle that I drew here, we can do the same thing. We can alternate around, and when we get back to the beginning, there's no problem. So the chromatic number of this is also 2. But notice what happens when we do this 5 cycle. Blue, green, we're alternating. But when we get back to this vertex that I'm going to color in pink, it can't be blue because there's a vertex that's connected to it at the top that's blue, and it can't be green because there's a vertex below it that's highlighted in green. So it has to have a third color, and this is true of all odd cycles. The chromatic number is always 3 because you can alternate all the way around except for that last one. And here's another graph where it's easy to see. I've got the complete graph on 5 vertices. The chromatic number of this, if we start coloring it, start with any vertex and any color, but now notice none of the other vertices can be pink because they're all connected to the vertex we just colored pink. So let's take another one and do yellow. Now none of the other vertices that are left can be yellow because it's connected to all of them, or at least it would be if I could accurately draw a version of K5. That's better. So we need a third color, but now by the same reasoning, none of the vertices that are left can be pink or yellow or orange. So we have blue, and then we have green. And this is true in general. The chromatic number of any complete graph is n. So the chromatic number of Kn equals n. Most of the time, there's no easy rule for knowing what the chromatic number of a graph is. Try it out, think logically, try and figure out where you need to start to take care of the most complex part of the graphs so that the easier parts with, say, perhaps lower degree are left till the end. So I hope this helps with chromatic